Thanks, Lucas, for the introduction. Let me thank Fernando for the opportunity to be here this wonderful semester. So let's see. So today I'm going to be interested in minimal surfaces of the Euclidean space. So the talk will sort of fit into a broader theme of index bounds, but for the results I'll present today, this will be the setting, and these surfaces, they would be complete and no boundary. Okay, so the kind of questions that I want to ask then is if one can somehow prove that the Morse index, the sort of variational properties of sigma, can control its topology. So some constant times the topology of sigma. So I'll, state this in more detail soon and also motivate it. But there is also, in particular in the case of R3, there is a related question, which is asking how much the index of sigma actually controls the geometry of sigma. So let me put that as the motivating questions. Okay, so let's see. So let's then set our notation. So these are surfaces in R3. In R3 there is no, by the maximum principle, there is no closed minimal surface. So they're all the sort of interesting objects. Of course, solving the Plato problem, you can get lots of surfaces with boundary, but there is, of course, the question of this, the ones without boundary. So they all have to be complete. And so let me state here the notation that I'm going to use. So here's the surface in R3, and for us, the Gauss map, it's going to be one of the main actors of the talk. So this is just a map from sigma to the sphere, the unit normal vector. And there is a fact that makes the theory in R3 be very, very rich. It's this fact that connects the variational problem with complex analysis, and is that the surface is minimal so in other words, it's a critical point for the area functional if and only if this map N is, well, anti-holomorphic. So let me explain precisely what this means. So it's not that this is against being holomorphic. It's basically, so when you have your surface in R3, just the fact that it's sitting there, it inherits in the product from R3. So it inherits a complex structure or a conformal structure from that in the product. In other words, a sort of a way of having a multiplication by I from tangent plane to tangent plane. And of course, S2 has its standard complex structure. So to be minimal will amount to this map be anti-holomorphic. It will be precisely this h equals 0. And the word anti here is really because h is 0. It means that the differential is changing the orientation. You have trace 0. So one of the eigenvalues is positive, the other one is negative. So you're changing the orientation. So that's all that anti means. So you can just think that it's a holomorphic map. Okay. Now, and of course, the index of sigma. So this is just going to be the maximal dimension of linear subspace of the smooth function of compact support, such that where the quadratic form Q, well, the second variation of area is negative definite. Okay, so here in R3 the second variation just it has this very nice form. This is the second fundamental form square, but because we are in R3, I can actually write this as plus 2k phi squared. Okay, so I'm writing it this way on purpose. Usually when we're introducing this in for closed surfaces, you already go to the eigenvalue problem. But I want to somehow point that because the surface is non-compact, we somehow have to associate this sort of geometric picture, right? This two eigenvalue problem. So that's going to come, but we're going to have to work for it. Okay. Okay, so let me start with some motivation for this kind of question. And so this first motivation is going to be very naive. And it's basically because if you somehow have your surface in R3 and you have a topology somewhere, you have a neck, let's say. So let's say this is a neck sigma. Well, that neck, it's somehow telling you a direction where you can decrease the area, right? So if we just squeeze the neck tight, so we can decrease the area. So somehow, if you indeed have a lot of topology, you can imagine that you have a lot of necks, and that should force the index to go up. So that's the like say the naive picture, and I'll explain why. Because with an example, which is the Costa surface. So this is a surface that was constructed by Celso Costa in 1982. It's an important surface because in the history of minimal surface in R3, and let me just recall that briefly. So this fact was discovered in the 19th century, and in fact, you can use it to construct locally examples of minimal surfaces, right? There's this the Weierstrass data representation, which allow you to, if you have the right data, at least locally, you can construct a piece of a minimal surface. But somehow, if you want to get something complete, you have to understand how these pieces will come together. And so there is a lot of examples done in the 19th century using that, where you would get a periodic minimal surface. So somehow they will understand how to match this piece with somehow close it up together. And in the process, what you get is something periodic. Okay? And they were all embedded examples. There were some immersed too, but of course, people were really interested in the embedded ones. But aside from, they're all periodic somehow. So in other words, they all had like infinite geometry. So we can say that in terms of the total curvature. So if I integrate the total curvature, I get something infinite. And this was the case for all surfaces except the plane, the flat tube plane, the catenoid, and somehow there's the helicoid, which is obviously it's the surface where you take this axis x3, and you take a line and you start rotating around like that. So it's like a parking garage sort of structure, right? And it is periodic, so in some sense, but it has a topology of a plane. So all the examples with, let's put it this way, with finite topology, there were only these three. And this was up until 1982, where another example of a complete minimal surface embedded in finite topology was found. So that's why it's a pretty important example. And for the purpose of illustrating the index problem, it serves quite well. So it's a surface that looks like this. So you have a torus. So this is going to be, so it's conformal to a 2 torus, but with 3 points removed. And these points will correspond to these ends. So it's going to be a catenoidal end. So this looks like a catenoid. It grows, the height grows logarithmic with the distance. A planar end and another catenoidal end coming down. Okay, so let me write the topology of sigma. So this has genus 1 and the number of ends 3. Okay, but somehow we see a lot of necks somehow. Let's see. So we see this neck here because of the way it sits right in R3. There is this neck there, and if you believe me, there is a neck down here below this picture. So you would say, well, okay, so then the index of this guy should be 3. Okay, but it turns out there's a calculation of Nayatani from early 90s. He shows that the index of this surface is actually 5. So where are these other directions, right, where we could decrease at least geometrically it's hard to see them. And another point that I want to make with this example is that if I take a ball of radius r here large enough, somehow to remove all these sort of necks from the picture, if I just look at what it's outside, if I look at this guy here, this guy there, there is of course this other piece, right? Oops, too large. Then there is what it remains here below. Okay, so let me just bear with me here a second. So this part of the surface, it's pretty clear from the picture. It's graphical over this x1, x2 plane. And because if it's graphical, it means that when I look at the second variation, it's stable. I cannot decrease the area. So somehow there is no sort of movement that I can make in this blue region that would decrease the area. So the index must be somewhere all in here, but all I can see are this 3 ways of decreasing area, but somehow the index is 5. So that's why I call this sort of the naive picture. Okay. So, but still, so let me just write this because this is going to be important for later. So note, so sigma minus a ball of radius r, where r is big enough, is stable. So then there's this question, how the ends enter in the index calculation. Okay, but okay, so now with this example in mind, let me give you a sort of like less naive motivation. Why, even though there's this issue of the ends that somehow they're stable, we don't know how they're going to enter in the in the index calculation, but still there should be a bound that like this that controls everything. Okay, so this motivation comes from the Gauss map. So really, so what is the relation between the topology and the index? It's somehow both are very much related to the Gauss map of the surface. So let me explain that. So the sort of easiest to see is the topology. So if somehow I know suppose you give me a minimal surface, well, but actually instead of telling me what it is, you just tell me what n is. Can I recover its topology? Okay? So, well, I can at least say the following. So this is at least, let's assume for now that the surface is embedded. Otherwise, I have to adjust the formula a little bit. So the Gauss map, if I take the degree of the Gauss map, in other words, how many times the Gauss map is wrapping around the surface onto the sphere, this is just this integral, the integral of the Gauss curvature. And it turns out that this is genus plus ends minus 1. So let me introduce this notation. So this is genus, and this is ends. So sorry that G is not a Riemannian metric, but we just had a GR talk, so I guess it's okay. Okay, how about the index? So somehow I will make the same claim about the index of sigma. So, which is that if I don't know what sigma is, but if I know only what the Gauss map of sigma is, I still should be able to infer some information about the Morse index of sigma. So let's see. Okay. So let's see how I'm doing my notes. Yes. Okay. So for the index, what I'm going to do is I'm going to consider two metrics on sigma. So the first metric, that's sort of the natural one, is to take the Euclidean metric and just restrict it to sigma. But the Gauss map allows us to take another interesting metric on the surface, which is I would take the round metric of, so n is sending, it's a map to the round sphere. So I'm just going to take the round metric on S2, and I'm going to pull back using n to sigma. So this is the round. And the point is that these metrics, they're obviously they're different metrics, but they have something in common, which is that they're conformal with each other because the surface is minimal. Okay? So so let's see what we can do with that. So for instance, if I then want to calculate the index of sigma, somehow I have to look at the index of that quadratic form, this one right here, which is obviously calculated using the metric h. So let me write q of h, right? But somehow, because of conformality, this is also something special about dimension 2, the index of this form will turn out also to be equal to the index of q of h bar, where q of h bar is this form grad so in other words, I changed the energy. So I'm changing here the gradient. Instead of computing with respect to the metric h, I'm computing with respect to h bar. And I got away with this k, which is really, this is the Jacobian of changing from one metric to the other. So that's why this becomes true. Okay? So why would I be interested in doing that? Well, it's because this metric h bar has constant curvature equal to 1. It's the metric of the sphere, right? And basically, if I want to understand the eigenvalue problem for Q of h bar, I have to understand the eigenvalues of that metric, which are less than 2. So somehow I transforming my problem from just from finding the index of some general quadratic form to a form with constant curvature metric, and I'm interested precisely in the eigenvalues less than 2. So it almost sounds like too good to be true, and it is. There is an issue here, which is that this metric h bar, right? So branch points. So what are the branch points? So these are the points where the differential of the Gauss map is not full rank. So in those points, this metric h bar is not well defined, right? So in other words, so this makes h bar has singularities.
What happens in the Costa surface?
In the Costa surface, yeah. So this is actually how Nayatani does the computation. He takes the Gauss map, he looks where the branch points are, then he starts deforming the Gauss map and keeping track of everything, and then he sees when he can somehow calculate when the eigenvalue passes to positive. So so you get a nullity. So he somehow, every time through this deformation, you get eigenvalue passing from negative to positive. So that's how he counts the index to be 5. So you can do in the Costa surface. So it's not a totally naive method. I mean, Montiel and Ross also use this to prove and calculate the index of some examples. But for the general problem, there's no hope, because if you give me a general minimal surface, there's no way I can tell where the branch points are going to be. Even if I look at the picture, I mean, it's kind of tricky to tell what they are going to be. So so I call this the last naive point. It's still very useful. Okay. So let me mention some of the previous results containing index bounds for minimal surfaces in R3. Okay. So I don't know. Can you guys decide see here up until when? Here is okay? Yeah? Okay. That's good. Okay, so previous results. So I guess, so again, minimal surface in R3, it's a topic that has a very, very long history. It goes all the way back to Euler, Lagrange, and 18th century. But I'm going to focus here somehow in the results that are related to understanding this question of the index. Okay, so I guess the first one that really comes to mind is this result by Fisher, Colbury, Shang, and independently Ducarmo, Peng, and Pogorilov. So this was all around 1980, and where they showed that if I have a two-sided minimal surface, which is then, if it's index 0, implies that sigma is actually flat. So it's so the only possible guy with no way of decreasing the area is the flat plane. Okay. Okay, so So another, so I'm going maybe here for chronological order. So the next result is this paper by Fisher and Colbray, which is from '85, where she answers this question about what does it mean to have finite index, at least quantitatively. So again, this is for two-sided surfaces. So a minimal surface has finite index if and only if the integral of the Gauss curvature is finite. So in other words, if sigma has finite total curvature. Okay. So the idea somehow for this problem is basically if I have something with finite index, it means that, okay, so I'm going to start at a point, and I'm going to look at the surface intersect a small ball. So just like a geodesic, you can argue that, that a sufficiently short geodesic has to be minimizing. You can argue that if it's sufficiently small, for example, if it's a graph over the tangent plane, right, then that's going to be stable. Now, the second I start increasing that ball, the surface gets more complicated. It ceases to be a graph, right? So I pick up an index, then I pick up another one, pick up another one. So, but if I'm assuming that the index is finite, there has to be a radius where that stops. So the index doesn't increase after that. So in particular, outside that region, the surface has to be stable. So, so the ends of the surface, in other words, they have to be nice. They have to behave well. So that's sort of the idea, the starting point of this. So somehow you say, okay, so now the ends are nice enough. The curvature has to decay sufficiently fast. So we have this. Okay? Yes? For what? Not now, but yes. Because for one-sided surfaces, you're not allowed to plug in any function in the sec variation. You can only apply functions that, the way you look at the sec variation for two-sided guys is you look at the double cover, right? And then in the double cover, you have the second variation. And you know that that's going to be non-negative, but only for functions that are, anti-invariant. So then so this proof, per se doesn't work. So there is another proof, yes. It's coming in 20 years or something. Okay, so the next result in the literature, as we think about a 2-hour lecture, you have no excuse for not citing everybody, right? So this is a result by Tisk. So it's a very interesting paper where he actually shows, again, assuming that the surface is two-sided, that you can bound the index from above by a constant times the total curvature. So 7.7 negative. Okay. So somehow, if you have a control on your curvature, basically you're controlling the topology of sigma, and once you control the topology, you control all possible conformal classes that sigma can have. So that's sort of the idea. And once you have that sort of control, you have to control the index, because the index is related to, is invariant under the conformal classes. So it's so in other words, an upper bound on the index, it's something not so exciting from this point of view, because if you control the if you fix the topology, you are basically limiting all the conformal behaviors that your surface can have. So then it just kind of follows for that the index has to be limited to.
So it has
That's a good question. So yes. So Agiri and Mikalev, they, let me put a parenthesis. And this is actually the point of view, AG. Mikalev, around 07, they, 2007, they improved the constant. But unfortunately, it's still not sharp on some examples of families, so it's not clear yet what is the best constant. Okay, so let's see. Yes. So that's actually so. The point of that question that I was asking, so somehow this is equivalent to controlling the index from above by the topology. So if you somehow can do the opposite, which is control the index from below, right? And you use this formula here, then you actually can get that inequality. So that's actually one of the motivations also for that question that I posed, question 1. That I'll come later. So I just got a couple more results before I get to where I want to be. Let's see. So the next result is this Lopez and Ross estimate, which says that if you have a surface of index 1, so again, assuming two-sided, so if I have a surface of index 1, then it has to be, so there's only two possibilities, the catenoid or the Enneper surface. And I'm gonna dare to draw the Enneper surface. Let's see how that goes. So this is embedded, so if surface, and this is a immersed surface. And if you restrict yourself to embedded, then okay, index 1, you get the catenoid. So it's sort of the natural improvement from that theorem of Fischer-Kolbe and Shen. So the catenoid is just the it's minimal surface of rotation, right? So x1 squared plus x2 squared equal to cos squared of x3. And well, Enneper is a little harder to draw. So I'm going to try to draw it just before it starts self-intersect. So it sort of looks like this. So yeah, I knew I wouldn't do very good. So, but it's basically it looks like that. This is just before it keeps coming this way, and then it starts self-intersecting here, right? And then there is also another self-intersection on the other side. Okay, but the topology is very simple, so it's simply connected. It's just that somehow the way it goes to infinity is spiral to itself. So this is immersed. Okay. So I already mentioned Nayatani's results, so let me skip to the next one, which is Ross 2006. Oops, I forgot an important one, sorry. Okay, so This is a paper by Choi from 1990. So this was a interesting paper where, so in Riemannian geometry, you learn this basic principle about the Morse index theorem, which says that if I have a geodesic long enough, right, okay, it's going to be unstable because it's too long, right? So, but somehow I can also define the Morse index in a similar way, and I want to count that number. And there is a theorem that says that one way of doing that is just go along and counting the number of conjugate points, right? So, so Choi, he did an analog of that. So he proved that the index of a minimal surface in R3, it's greater or equal than what he called the Vision number of a certain appropriate Jacobi fields minus 1. So, so I'll talk more about that if I can at the end of the talk, but the idea is roughly is that because the surface in R3, you can, for example, you can take, let's say, an axis, right, x3, and you get the rotation infinitesimally doesn't change the area, right? So it's going to give you a Jacobi field. Now, that Jacobi field is going to be parts of the surface where it's tangent, right? So it's going to split up the surfaces into pieces, right? So, whereas in a geodesic, it's pretty clear what it means to be a conjugate point, right? So here, what we have is you have this Jacobi field, which instead of just being 0 at a boundary point, right, it's 0 in these regions of the surface, right? So that's why he can't really get an equality like in the Morse index theorem for geodesics, but he's able to get this inequality and prove some. I think he recaptures this theorem, he recaptures that one using this point of view. Okay, so it's not really, so this is somehow it's an adaptation of the conjugate point. So it's sort of like okay. Okay, so now let me then mention the next result. Which is, okay, so this brings me to this paper by Antonio Ross, which was really the paper that sort of got us started in the problem. We started reading this paper and had some ideas from it. So what did Ross prove? So Ross, he was really he was trying to prove this, trying to classify one-sided stable minimal surfaces, show that they do not exist, and understand that problem. So he came up with a method which is intrinsic and is robust enough to work on the double cover. And as a byproduct, so he not only proved the results he wanted for one-sided minimal surfaces, in the two-sided case, he came up with a novel index bound. So what did he say? So if it's two-sided, so Ross proved that the index of sigma is greater or equal than 3g over 3. And for one-sided, he showed a couple things actually. So he showed that he proved a version of this theorem, which was unknown. So that the index is finite if and only if has finite total curvature. He also proved that there is no stable one-sided minimal surface. And finally, he proved a version of this bound showing that the index of G is at least G over 3. Okay. All right, and then after this paper, we were able to show the following result a few years back. Was that if we have a sigma, again, two-sided, doesn't have to be embedded. Here, there's no assumption about embedded, this is just immersed. Then the index of sigma is at least 2/3 G plus R minus 1. Okay. And let me say the sort of idea, the sort of technique that Ross used, it's robust enough, as you see, that, well, at least when you have ambient manifold with sufficiently nice curvature, right? Or some, unfortunately, it doesn't work in all manifolds, but for instance, you can prove index bounds using this similar method for metrics on the sphere, minimal surface of the rounded sphere. So this was done by Savo. So Ambrosio, Carlotto, and Sharp, they also show an index estimate where you have minimal surfaces of a general manifold that you can embed into Euclidean space, and you impose an assumption on that embedding. Then the method gives you a bound as well. They also did that for free boundary minimal surfaces. There is, further work by Esky and Mendes. So one can do. There were quite a few theorems proven in that direction. Okay. Okay, so now, so this theorem, it solves this question that you asked, that Francesco asked, that, so what can you actually prove something like this? So that because at least if I have an embedded surface, I can relate this linear term here to the integral of k, right? And then I will end up with something like that. So this was one of the applications of our result. But if you are interested in the general problem, in particular for immersed surfaces, then this bound is very bad. So let me show you why. So for example, so the remark, so this bound, let me call it star, it's not very good for immersed surfaces. So for example, there is a generalization of the Enneper surface. Can't believe that I erased it. So this is the kth order Enneper surface. So how does this surface look like? It has very similar Weierstrass data than the Enneper surface, but you put a power k on the Weierstrass data. So it means that instead of just wrapping around a few times as it goes to infinity, it wraps around k times. Okay. So if you try to look at the intersection, of the Enneper surface with a ball, it kind of goes up, down, and then up, down. This one goes up, down, up, down, up, down, up, down a few times. So that's sort of like how it looks like. And this surface has index known to be 2k minus 1. So this is a calculation by Montiel and Ross, 92. But it has Gina 0 and R equal 1. So the right-hand side here is negative 3/2. Right, so so for the point of view of embedded surfaces, embedded surface, this is fine, but because you really have embedded in, so but if you have a merged surface where your end wraps around many times, you're just accounting for one end. You're not accounting for the number of times the end is wrapping around itself, right? And of course, that's going to enter in the calculation of the total curvature. So, okay. So recently, we proved this result to immerse surfaces somehow accounting for the multiplicity of the ends. So we show the following. So again, this is okay. So suppose sigma, it's a two-sided minimal surface. With genus G and R ends. So let's suppose that the ends have multiplicity D1, D2, all the way to dr. So what is the multiplicity of the end? Okay, now obviously these index estimates, they only make sense when this number here is finite, right? If it's not finite, then there's nothing to prove if this is infinite. And once you know that this is finite, you know by this theorem that the integral of k is finite. And the integral of k being finite, you don't know, you have no quantitative, you don't know how big it is, but just being finite, being a surface with finite total curvature, it tells you that the ends cannot be too wild. In particular, the Gauss map, the normal vector field, has to converge to something. Even though it's wrapping around, right, the normals, they have to converge, okay? So in that case, how do you define what is the multiplicity? You basically take that end, right, which is wrapping around itself, you intersect with a very large ball, and you have a curve, right? But because the normal vector field to those ends is converging to a vector, those curves, they have to converge to a great circle as you blow them down, okay? And that great circle, of course, that curve, right, that intersects sigma with the end, sigma intersect with the end is going to be a curve wrapping around, but it's converging to the circle, so it converges with an integer multiplicity. So that's what these numbers D1, D2, dr are, okay? So I'm using this fact that very important fact that the integral of k is finite. Okay. So then the index of sigma, it's at least 1/3 of 2g plus 2 times the sum of dj plus 1, j from 1 to r minus 5. Now, one interesting thing that we noticed when we were trying to prove this, we had to understand better how our method worked near an end, is that we actually saw that this bound here, when the surface is embedded, this theorem actually improves this one. If you plug in dj, all of these equal 1, so that's what happens when the surface is embedded, right? So the ends are embedded, the normal vector field converges to something, right? So the intersection is just going to be, with a large ball, it's just going to be one curve. So these numbers are all 1. So we get here, let's see. So I'm going to just write it in blue here. So in 18, right? We actually get that the index is greater or equal than 2/3 g plus 2r minus 5. So assuming sigma embedded. Or more generally, just assuming that sigma is a merged surface with embedded ends. Okay? So this was surprising to us because, you see, the contribution from the number of ends here, it's linear, but it's with a, with a coefficient bigger than 1. That's minus. This is sort of like a residue from the method. 5/2?
Yeah, because you put the 2 outside of everything, so it just...
Oh, did I? Oh, okay. Yes. 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 Okay. But it still beats this one. Okay. So it was a bit surprising that the number of ends were, But I should say that there is this mysterious thing, like for embedded minimal surface in R3, there should be a relationship with the number of ends in the genus. You cannot have a lot of ends without having a lot of genus. There is this conjecture, the Hoffman-Mees conjecture, right, that somehow they're related. So I won't always go as far as say that, from the perspective of this bound, it seems like the number of ends, it's somehow having more weight than the genus, but it's mysterious. Okay. Okay, so another so even if you really don't care much about immersed surfaces, sort of this result can say something new and interesting for embedded one as well. But I just want to point out a motivation for studying immersed minimal surfaces, this sort of estimate So the first thing is that the method, it's purely intrinsic. So even though we don't really use that, like even in this theorem here, we don't use embeddedness, right? But there is also, so this just from the point of view of analysis, even if you have a immersed minimal surface, you pull out the metric from R3, and you look at the second variation of area, right? So you have the Laplacian, and you have this other term, which is it comes from the second fundamental form. So it's a Schrödinger operator on the on that surface, and you can just look at it from the point of view of Schrödinger operator theory. You want to understand the sort of spectral properties of that operator. Of course, it has a geometric background, right? Because it comes from a geometric problem. But from the point of view of the theory of Schrödinger operators, when you have just the Laplacian, your spectrum can be anything, really. You have only essential spectrum. But then you add a potential term, which in this case is the Gauss curvature, and it comes with a sign. The Gauss curvature has a sign. So what does that do to the spectrum? It takes the essential spectrum, it sort of shifts, so it's 0 on, but you could have some discrete eigenvalues missing. So you're going to have that every real number after 0, it satisfies an eigenvalue equation, but there are the ones that are negative. And those are the ones that somehow physicists are interested. Because so if you put this problem for minimal surface into that perspective, then the following question is very natural. So this was a question from Gregorian and Yao, was that if I take sigma any immersed minimal surface in R3, then there exists a constant positive. I mean, obviously, let me put it this way. Then the index of sigma is at least a constant times this integral here for some universal constant positive. So if I want to write it like that, maybe I should put like any immersed non-flat minimum. Because I don't want to have to be 0, right? 0 greater than 0. So this question was actually the sort of motivation for looking into the immersed case, and then we realized that it also had some due consequences for the embedded problem. Okay. All right. So let me the last 2 minutes just say a little bit about what are the sort of scheme of the proof, especially how it compares to the result of Ross. Okay, and then we can take a break. Okay, so Ross's proof has this key lemma. So basically, the idea is in all these sort of index estimate problems, when you want to write explicit bounds, is like, what are the good test functions that you can plug in the second variation, right? And the problem is that when you have higher index, you really don't know anything about the first eigenfunctions. So constructing test functions that are going to be orthogonal to that, it's not clear what to do, right? So Ross, he has this lemma from which one can build a lot of test functions. So let's see. So let's take a surface. So I'm going to take a harmonic one form over sigma. So this is harmonic for the Hodge Laplacian, okay, the usual. So let's take then the dual vector field to that. So write x w. So this is the dual. Well, this is nothing more than this vector field here in R3. So this guy. Okay, so it gives me these functions. Okay, so this is just in the product of norms. So then he showed that this vector field satisfies the following Bochner type inequality. So is that the Laplacian of this minus k times that, I think there's a 2. This is equal to W dot A. So note, this is a vector equation. So in other words, for each of these coordinates, so this is a vector field with 3 coordinates. For each of them, I have that the Laplacian of the coordinate minus 2k times that coordinate is equal to this function times the first coordinate, of the normal vector field. Okay, so he proved more too, which is important. So moreover, he understands the case. So somehow, so moreover, this is 0. No. If and only if omega is in the span of these forms here. Okay. Okay. So let me just make the remark. So obviously this has somehow a connection to the second variation by just looking at this formula, right? Like this looks a lot like the Jacobi operator, and in fact, if I take Laplacian of x omega minus 2k x omega, and then dotted that with x omega, well, this is going to be equal to this. And this is 0. Because this is a dual vector field. This is a tangent vector field. And this guy is the normal. So it is, in some sense, it's like a weak Jacobi field somehow. Okay. Okay, so this lemma, it's basically a calculation that done in Ross. So let me show you how he proceeds from that. So suppose we want to prove process bound, right? Which that the index of sigma is greater or equal than this. Okay. So what you're going to do is, so suppose not, so suppose it is false. So that the index of is less, 3 times the index is less than 2g. Okay. Now 2g is precisely the dimension of the space of harmonic 1 forms on sigma, which are in L2. Okay, because if they are in L2, they have to go to 0 at the end, so it's kind of like the ends were not there. So it's like you were in a closed surface. So the dimension is just 2g. Okay, so if that's the case, then I got a lot of harmonic forms compared to the index. So I can find one. So this implies I can find omega such that x omega satisfies the following, such that 1 omega is in L2, and 2 x omega, it's orthogonal to the index of sigma. So let me put this into quotes, because I haven't made that precise yet. So somehow I have so many harmonic forms compared to the index that I can find one where I can be orthogonal to the index, right? And if that's the case, then this implies that the second variation applied to this guy is greater than 0, right? But then you work out what this would entail, and you get that this guy, it's an actual Jacobi field. So then this is 0. So this implies that this has to be 0. But then this implies that if that is 0, right, by this part, omega has to be in the span of these functions. So what is that saying? That is saying that there is a function in here. There is a harmonic form in here, which is in L2. But that's impossible for a minimal surface in R3, if you think about it a second. These forms, they actually, they cannot be in L2. They have to grow, okay? So, so he gets a contradiction, okay? Now, so what is the idea that started our work was that, well, there are lots of harmonic one forms on an open surface, of course, right? I just have to prescribe something at the boundary. So, so if I just say that they are in L2, in other words, that they go to 0 at the boundary, then I get this many. But maybe I might allow them to be borderline L2 at the boundary. So I have a pole. I mean, not at the boundary, at infinity, right? As I go to the end. So they can have a pole there. But it turns out that you can actually let it have worse kind of growth as we go to infinity. And you can somehow adjust to pick up the multiplicity of that infinity. And then somehow you have to make this machinery go through. So that's what we're going to do after the break. So to prove the main theorem of the paper, it's really and it really amounts to understanding how one can push this method here to allow for more test functions. So the idea, so use harmonic forms, one forms that are not in L2. Okay, so what we're going to do is we're going to define this space L2 star. Okay, so let L2 star of sigma to be just the completion of the space of smooth functions with compact support, right? So that's usually how we define the spaces. And then with respect to this following norm, let's see, so integral I'm going to write it like that. So it's the integral over sigma times f squared 1 plus this. So we're going to put this quadratic weight, and we also need a logarithmic rate. Let's see. D sigma. So here, this absolute value of x, this is just the Euclidean norm. You know, of sigma in R3. Okay. So in other words, we're using the extrinsic distance, and it's a luxury we can make because when proving these theorems, we may already assume that the surface has finite total curvature. So we have like nice properties like properness and things like that. So there isn't much difference in working with one norm versus the other, but this norm is it's slightly more convenient for us. Now, if you're thinking here about the weight, so what this weight does, it basically allows us to integrate constants. Okay, so so this is sort of motivation for this is precisely that this derivative here Wait. R minus 2. And so I know here we have a r to the minus 1, here we have a r to the minus 2, but then there is a factor r here from the area element, right? So this is sort of the motivation for this weight. Okay, and so before going into eigenfunctions and the first thing that we should check, instead of going to any further analysis statement, is to count the number of forms that what kind of forms this space allows us to integrate. Okay, so let me make this proposition. Any questions? It's a Hilbert space, right, with this norm, so it has nice properties. Okay, so suppose that this is the parametrization of an n, so a conformal of an n ej in sigma. So this is the disk, right? So assume that z is the is the coordinate here, local coordinate. Then the forms dz over zl for L equal 1, 2, up to the dj plus 1. So where dj is the multiplicity of this end, ej. Okay. All belong to L2 star of ej. Okay. So in other words, this is saying that, so if I actually were working with forms that were just in L2, then I could actually not look for forms like that, right? But because I'm working in this weighted space, not only I get dz over z, but I also can go all the way up to the multiplicity plus 1. Okay? So let me just do a quick calculation here just to see why this is not, it's less mysterious than it should be. So if I look at just C, right? So another remark. So if I have just the conformal plane, right? And I'm parametrizing the infinity with conformal coordinates like that, this is just taking w equal 1 over z, right? So let's say that these are coordinates in C, okay, near infinity. And then I look at z equal 1 over w for coordinates for the infinity at C in the disk minus the origin. Then dz over z squared, this is just let's see, d1 over w over 1 times w squared, right? this is W squared D. Okay? But then, if I differentiate this, right, I get, this is just, so that's just minus dw. Okay, so in other words, this has multiplicity 1, so dz over z squared would correspond to L equal dj plus 1. Right? So going all the way up to the multiplicity where dj is 1. So this form looks like very bad from the point of view of the conformal parameterization, but from the geometric point of view, just like it's a unit. It's a norm 1 form, right? It has geometric norm 1. So in other words, the fact that I'm able to integrate dz over zl all the way up to here, it's more or less using this method will come from the fact that this norm can integrate constants. Okay?
So is it clear that this is the best you can do, but you can
not clear yet, no. Yes, but I think so. In the original paper, we did this and we thought this is very good, this is very cool, right? But then we saw that if you really push the logarithmic cutoff trick, right, what it really allows you to do is to integrate constants with finite energy, right? Because it converges to 1 with finite energy. So that's sort of the idea. So I think maybe this is the best one can do, like integrating constants. But I'm not, I've been surprised before. Okay. So this is just a calculation. Let me save it here for later in case I have time. But it's sort of illustrated in that. Now, obviously, I mean this lemma is still true, right? This is a pointwise calculation. It only uses that the form it's a harmonic 1 form. So what that proposition tells us is that if we can count then the dimension, so proposition, the dimension of H1 sigma intersect, this is equal to 2 G plus dj plus 1 J like that. Okay, so this is really the extra information we are getting from considering these other norms than what Ross had here. Right, so let me show this. Pretend we are all algebraic geometers. Okay, so we have the surface which is conformal to Riemann surface of genus G, and it has R punctures. Right, so I'm looking for the space of we can basically consider holomorphic forms instead of looking at harmonic 1 forms. Then we can take real and imaginary part. That's actually where this 2 is going to come. So let's just focus on holomorphic 1 forms for a second. So the fact that we have genus G, that gives us 2 G parameters for a holomorphic 1 form. Now for each puncture, I'm allowing a pole, right, all the way up to this order. For each J, I'm allowing a pole of order 1, 2, 3, 4, or all the way to dj plus 1. So this gives me another this much of parameters to construct the holomorphic 1 form, right? And the question is where this minus 1 comes from. Somebody has a guess? It's for the poles of order 1 because of the residue theorem. So whenever you look at holomorphic one forms where pole over the 1, pole over the 1, pole over the 1, all the way, right? Poles over the 1, they have a residue. So you kind of look, you have to have that residue be 0. So kind of, they're not linearly independent. So you lose a dimension there. Okay. Okay, so we have the forms that we want to plug in. Now I have to go into the sort of technical side of the proof, which is this statement that somehow I have my quadratic form, right? So far we even didn't talk or define what eigenvalue problem we are looking at, right? Or what eigenfunctions are going to be, but somehow I'm saying that if I have a vector field that is orthogonal to the index, this is the sort of the rough idea, then I can draw that conclusion. So what Ross really uses is this result. So in L2, so we have this following proposition by Fisher and Colbury when she proved that finite index is equivalent to finite total curvature. So we're basically saying that if I have a minimal surface of index k, which is finite, okay, then so this statement is just saying that that quadratic form is negative definite, like the maximal dimension of a subspace, right, of L2 intersect compact supported variations, okay? Where that quadratic form is negative definite has dimension k. So if that's the case, then there exists smooth functions f1 all the way to fk such that 1, they are L2, f are orthonormal in L2, sigma. 2, they satisfy the eigenvalue equation, Laplacian of fi plus 2k fi let's see, so it's minus plus lambda I fi, it's equal to 0 for some lambda 1, lambda 2, lambda k negative. And finally, 3, if I take a smooth function with compact support, okay, intersect the that it's orthogonal to these functions in L2, so that I take the span of these eigenfunctions and I look at the orthogonal complement of that, then Q of phi greater than 0. Okay. So this is the proposition that that we want to use. You see here, basically, this is saying that we have eigenfunctions. They satisfy equation. They are L2 orthonormal. They are not necessarily of compact support. Actually, they don't have compact support. They go all the way to infinity. But somehow they pick up all the index such that if I look at a compact supported function orthogonal to those guys, the second variation is non-negative. Okay, so this is what is used in here, one has to be careful because we would like to plug in x omega, right? But x omega does not have compact support necessarily, even though it's in L2, right? The omega is in L2. Even in that case, the entries of this vector field might not have compact support, right? They might just decay. So I can't quite, just because I'm saying that they're going to be orthogonal to the eigenfunctions, I can't quite conclude that. I have to somehow do some approximation with with test functions. But and that sounds fine. But the reason I'm stating that now is because now we're going to extend this proposition to these functions that are not in L2. So this is going to be an issue when we come down here, right, to apply the same thing. So what is the proposition that we proved for L2 star? Okay, so again, suppose you have a minimal surface with index less or equal than infinity. So this is the usual index, okay? So then there exists smooth functions f1, fk such that they are orthonormal in L2 star of sigma. 2, they're going to satisfy the eigenvalue equation. So the eigenvalue equation like this, plus lambda I minus I keep minus 1, yes, log squared fi equals 0. Okay, for some. So let me put it as a question here, maybe different. Lambda 1, lambda k less than 0. And finally 3, I have the same property. So if I take any smooth compactly supported function and I intersect that with the orthogonal complement, and here is the complement with respect to the L2 star in the product, okay, then this happens. Okay, so so the reason why the eigenvalue equation here is different is just because in the Rayleigh quotient you have Q, which is the same quadratic form, but now you're going to divide by, instead of dividing by the L2 norm of U, right, minimizing that, you're minimizing by the L2 star norm of U. So when you do the variational characterization, right, you end up with this term in your equation, and it's actually a mystery as far as I'm concerned whether these numbers are the same. I've seen papers in Schrödinger theory where one shows that they are the same. If you think about it, what you're doing is you have the same quadratic form, you're just diagonalizing it with respect to different in the product somehow. So could the but in this case I have no idea. What is key for us is that the number is the same, obviously it's k, it matches this sort of variational index, and we have this property here. Okay, so let's see. So I maybe can ask the audience to see. I might not have time to do both, explain this bit here or prove this. So what would be preferable? Uh,
What's the alternative?
no, proving this, right? Or assuming this, and then just show, because here, well, here there is a, I can tell you so that you guys can choose better. Here, even in Ross' paper, so there is a little problem here, which is you take your function in L2, like I said, right? Then you have this vector field, your harmonic one form, you have this vector field, you want to say that is orthogonal to the index, but this does not have compact support. So I can't use this part 3 immediately. Somehow you have to deal with that using test functions. And my claim is that log cutoff functions, you know, they just work. And you somehow can make this claim that this is still going to be greater or equal to 0, even though this guy does not have compact support. It's believable, right? And then once you have this, you really use the formula that it satisfies to conclude this, so you get that omega is in the span. Now, in Ross' case, because he was working in L2, he gets a contradiction right here, right? But right here is, okay, there's a contradiction. This function, this one form, they cannot be in L2. In our case, what do we do, right? So we basically say, okay, if the index estimate is false, right? So if 3 index is less than, where is it? This 2g plus 2 times this j equal to r. Oh, I don't know why I keep putting this parenthesis, minus 5. Okay, then we can find omega such that, so here I get, there is a reason why we have the minus 5 here. So 1, this form is in L2 star of sigma. 2, this form, it's not in the span of these guys. So I have to remove them. So Ross did not have to remove because they're not in L2. So if you are just L2, it's fine. They're not there. But once you work with this space, these forms are there. So if you just, so you won't get a contradiction, right? So you have to remove them. So that's why in our estimate we have this this term here. And finally, x omega is orthogonal to the index of sigma. So my claim is that you can construct, you can, if this happens, then you can construct omega satisfying this. And then the rest of the proof is more or less like Ross. You somehow show that even though this guy here does not have compact support, it might actually not be, it's not in L2, so it might actually, but it's not worse than a constant at infinity because it's in L2 star. So you can still, using log cutoff functions, test functions, you can show that you have this, and then the sort of proof is the same, but then when you get to here, you know that omega is in this span, right, by Ross lemma. If I have a vector x omega such that this happens, then the form has to be in this span. But this is a contradiction because I already removed those guys from the count. Okay. So, okay, so maybe let me do this proposition. Okay, so the whole point is that, okay, so we have here our surface. Let me just draw something like that. Let me assume that the origin is in the surface, so I'm just going to take a ball, then I'm going to take a ball of radius r. Okay, and let me take r large enough such that sigma outside the ball of radius r is stable. So sigma minus this is stable. So what is the idea? Well, if I take now a ball of radius rho, where rho is a large number, right? So this ball here of radius r, I'm going to pick it such that not only actually, let me say sigma minus this is stable plus the index of sigma intersect this guy is k. Okay, so I start at the origin, start taking balls, I start seeing some index until I'm in a large enough ball where there is already the index k of the surface. Okay, so in particular outside the surface has to be stable. Now let me take then a larger ball rho. Okay, so if I look at the if I look at the quadratic form Q in this ball of radius rho, right? I have actually two norms there. I have the L2 norm and I have the L2 star norm. Okay, but in this ball, because this is a finite ball, those two norms are equivalent there, right? I'm just the weights don't matter. Okay, so I'm gonna have then that the L2 index of the operator is the same as the L2 star index of the operator in the ball of radius rho. Okay, so in particular, so we can find, so this implies that there exists eigenfunctions, okay, such that they are eigenfunctions for the L2 star problem. So minus 2 fi rho plus lambda I rho. And then there is the weight log 2 fi rho. So let me do it 0 equal that. Okay, where f1 rho, sorry, these eigenvalues here, lambda I rho, they are all negative. And you have k of them. Okay, and moreover, this is a so what I do to find this? Well, I just look at the quadratic form, look at the L2 star norm inside this region, sigma intersect the ball of radius rho. Okay, and that's a Dirichlet problem. Okay, so the discrete the spectrum of the operator is going to be discrete. I just look at the negative number of eigenvalues, right? It has to be the same negative numbers if I had done everything with respect to L2 because the norms are equivalent. Otherwise, I can reach a contradiction. Okay. So in other words, for finite balls, these two theorems are pretty much the same, right? So the way you prove this theorem is you do this in L2, but here we're doing L2 star. Now, what you want to do is you want to send rho to infinity, and you want to say that those eigenfunctions, they're going to converge to something that will be the eigenfunctions you're looking for. Okay, but let's see what can happen there. Well, one thing that you have going for you is the is the fact that once I increase rho, these eigenvalues, they don't increase, they actually go down, right? So it's monotonicity of the eigenvalues for when you increase the domain, okay? So, but one thing that could happen in principle is that, okay, what if they go to negative infinity, right? Unlikely, but that's one thing to worry. And we'll see that this property here rules that out. The fact that you have a stability inequality outside this ball of radius R, you see when rho is very, very large, right? You have a stability inequality on a big piece of your of your surface, which is sigma intersect the ball of radius rho, right? So the eigenvalues, okay, they stay bounded. They stay between 0 and some negative number, k of them. Now, the other thing you have to worry, and this is more serious, is that somehow I make this rho to get larger and larger and larger, and this eigenfunction, even though they have L2 star norm equal 1, right? All these guys, let's just extend them to be 0 outside outside this ball, sigma intersect the ball. Then these guys, they have L2 star norm 1, okay? But they could, in principle, weakly converge to 0. In other words, this as rho gets very large, this function, they don't decay fast enough at this boundary here, and you have mass going away from infinity. So you're not going to get this, for instance. You can get that this, they're still going to satisfy an equation, which is fine. You see, 0 satisfies the equation. But fi equals 0 satisfies an equation like that, but it's no use for you. It's not an eigenfunction, right? So the whole point is somehow to control the norm of these fi rhos outside this ball. And again, the stability inequality that we have outside here is going to be crucial for us. So let me just point out what we proved there. Okay. So let's see. So sigma, it's minus ball radius r0 is stable. Okay. So if I take, so what does that mean? If I take any test function phi and another test function which is here, but it is supported, it's supported outside of that. Okay, so it's 0 in the ball. Then when I multiply that, I get that this has support of eta, where the surface is stable. So I have that this satisfies the stability inequality. Let's see. So then Q phi eta are equal to 0. So if we write down what that means, write phi eta squared sigma greater than 0. Okay. Okay, so let me now make a choice of eta. So I'm going to choose the usual eta for the log cutoff. So what is that? So it's a function that, 1 minus that, because I want this guy eta to have support outside this ball, right? So actually, I don't need it to go down to 0. I just needed to have that, because you see, I can actually afford this eta to go all the way to 1 at infinity, but still, if I multiply these two guys, they're gonna have compact support, so I still have this, right? So let me take this equal to 1 minus phi r, where phi r is the usual log cutoff function. So it's 1 for here. It's 2 minus log x over log r. Let's see. So for r less than x, r squared, and then 0 for this. Okay. So I claim that if I plug that in, that choice of eta, I basically going to get an expression for phi, which is any compact supported function that will tell me that these eigenvalues don't go to negative infinity. So what they tell is that okay, so let me just, I get an expression like this, phi r. So this in here, this is less or equal than 2 times plus 2 times a constant integral phi squared sigma r squared. Okay. So in particular, this guy, so I mean, I'm just making this sort of eta and plugging that in, and then I'm manipulating, expanding it out the Q, right? I get to inequality like this, and this is greater or equal than 0, right? So what it does, it basically tells me then that my quadratic form, this should be like this, var phi. My quadratic form applied to this function phi, it gives me a lower bound, right? So if I send this down here, this is a L2 term, but I can make this into a L3 star term by adjusting this constant, right? Because this is in the ball, this is in the ball of radius r squared. So the adjustments that I have to make, it's finite, right? Up to that ball of radius br squared. So I get that this guy is greater or equal than minus constant integral of phi squared, right? This is what I mean. So this is then greater or equal than minus constant, and then I can put like a 1 plus r squared minus 1 log 2 plus r squared, and then here integral of this guy phi squared, and then 1 plus this minus 1 log 2. Right, so I put this down there to account for this. So this is interesting because, okay, this is for any smooth function, right? So we get that this has to be at least that. So in particular, the eigenvalue for the rho problem, right? In the rho ball, this is rho eigenvalue, cannot be more negative than this. Basically, this is what this inequality is saying, right? Because if I minimize the Rayleigh quotient, I minimize Q over this orange guy. I put it here. And if I minimize that, this is going to always to be at least this constant. Okay, so the eigenvalue does not go to negative infinity, and this is due to the stability inequality, so that's good. So in particular, as I send rho to infinity, these numbers, they stay monotone and bounded. So they're going to converge to something, right? Now, what else do we need for us to make fi rho to converge? Okay, so maybe I'll erase Fischer-Skolber's. Erase this too. Maybe in a second. Okay, so this implies lambda I rho very equal to minus CR, you know, whatever that is. 1 plus R squared minus 1 log squared Q plus R. Oops. I squared, like that, yes. Okay. This also gives us a bound on the W12 norm of this function, so in the ball of radius world. So moreover, there's stability outside ball of radius R. We get that the integral of this guy see. So how do I get this? Well, I just plug in fi rho in here, and then I use that fi rho satisfies the eigenvalue inequality, comes out, okay? The lambda I. Then I use that the lambda I is at least this much. So I get an estimate like this. Okay. Now, I should say that it's important that this number here, that this bound is like that we have something like this, like it makes the sign work. Okay, so sorry, this is in the ball of radius R. Okay. Okay, so what can I do with this? So, well, I can do the following. I can take R big enough, fixed. Now I take rho, much bigger, and I send it to infinity. Once I send that to infinity, at least in this region, right, my eigenfunctions satisfies this W12 bound, which is independent of rho. Okay? And so because W12 in this ball embeds compactly in L2 star of sigma intersect this ball. So I get a sequence rho j, right, such that fi of rho j, well, I get a sequence of rho j's such that for those radius rho j's, the eigenfunctions, they converge strongly in L2 to something, at least in the ball of radius R. Okay? Well, sigma intersect the ball of radius R. So now what I can do, this is for R fixed. For R fixed, I have a sequence of radii rho j where I get a convergence here. Now I do for R slightly bigger, and I take a subsequence of this sequence that works for this radius, right? And a subsequence of that will also converge the ball of radius 2R to a function, okay? Then I do for 3R, let's say. So a subsequence of those rho j's that works for the ball of radius 2R will also converge in the ball of radius 3R. So the fact that this bound is blowing up as in R as R goes to infinity won't matter, because I get convergence for each ball of radius R, then I increase. Okay? Now, so this allows us to find these FIs. Okay. Now, the difficult part, which I won't have time to get to, unfortunately, is to actually show that these guys are not zero, that we have no loss of mass. So that part, somehow, just this test function doesn't work. Roughly what we need, we need to work with test functions that get bigger and bigger, what they see. So we got to put like an alpha here and an alpha there, so we get this dependence. So we're going to have estimates that do not go to 0. We need a bound we need somehow that the integral of f outside some ball of radius r alpha, and then the weight here, so we need this to be like 1 over r, right? So that when I send r to infinity, this goes to 0. But actually, you get something like O to the r. You get a constant like this. Oops, this is outside, sorry. So you see, we need to somehow say that the integral of these eigenfunctions outside a certain ball, it's uniformly small, right? But actually goes to 0 as the radius goes to 0. So that would imply that you have no mass going to infinity, right? And would give that this function here, that's L2 star norm 1. This is the L2 star. So we need this alpha because with just the r, you can actually make this term go to 0. So you have to send alpha to infinity as well. Okay? So thanks for your attention.